Hello everyone, welcome to the 8085 instruction set tutorial. In the last session we saw this data transfer group instructions from MOV to XCHG. Now in this session we will see the arithmetic instruction from add, ADI, ADC, ACI up to DAA. So these are the instruction, okay, uh, totaling about 14 instructions, okay, from ADD to DAA. So I have written now we'll study. First of all we start with ADD and ADC. Okay, so here I have written some code. The first instruction is MVIA 9C and VIB AB and so on. These are the codes. Okay, what we are interested is in this three instructions: add B, add C and ADCD. Now what does add B do? Add B, it adds the contents of register A with register B and stores the result in register A. Add C, it adds the contents of register A with register C and stores the result in register A. And this ADC, what is this ADC? This ADC, it adds the contents of register A with register D along with the carry which was generated in the previous addition. So suppose here if we are adding add C, doing this add C and a carry is generated, so it will also add that carry along with A and D and store the result in register A. Okay, now let us execute this. So with the first step, when we execute this first step, MVI A 9C gets stored in register A. With the next step, MVI B AB gets stored in register B. With the next step, MVI C E7, so E7 gets stored in register C. With MVI D 63, it gets stored in register D. Now with add B, what will happen? So this add instruction, it adds the contents of register A with any other register. Okay, so here it is register B, so what it does is it adds the contents of register A. This was 9C with AB and the result is 47 and we can see a carry is generated. Okay, then what we do is next instruction is add C. Now add C, it adds the contents, the new content is 47 with register the contents of register C and stores the result in register A. So this 2E is the content final, the next the sum. Okay, and we can see carry is generated. Now in this add instruction add C, it only adds the contents of register A with C and it ignores the carry which was generated in the previous addition. Now with the next step ADC, now what this add ADC do? It adds the contents of register A which was 2E with 63 and also the carry which was there in the previous addition, and we get this as the number as 92. Okay, and then finally we have the halt instruction. So this is how this instructions ADC and add works. Now let us see some more instruction, okay, with respect to is 8085. So in the first row, this is the first row of arithmetic instruction. We did this ADD and ADC. Now let us do this ADI and ACI. Okay, to understand this I have written the code. So we have the first instruction MVI A 7A, ADI AB and ACI 57 and halt. So what is MVI? Of course MVI will store 7A in register A, and ADI the full form is add immediate. It is a 2-byte instruction. What it does, it adds the contents of register A with this data AB and stores the result in register A. And what this ACI does, ACI means add immediate the data with along with the carry with register A. Okay, so with this ACI will add the contents of register A with this particular data as well as the carry which was generated in the previous addition. Okay, and store the result in register A. So let us run it. So with the first step we have this A 7A in A. With the next step this AB, it gets added with 7A and this is the result 25 and we can see carry is generated. Okay, so in this ADI only the data of A and the immediate data is added and carry is not added which was generated in the previous addition. Now with this ACI 57, what it does, it adds the contents of register A. Now the new content which was 25, it is added along with 57 and the carry which was generated in the previous addition, and we get this final sum as 7D. Okay, and this is the halt instruction. So this is how we have this ADI, this is add immediate and add immediate along with the carry. Now we consider the second row, that is we first study the two instructions SUB and SBB. So for that purpose I have written this code MVI A9 for MVI B8 for MVI C7 0 MVI D 06 sub B sub C and SBBD. Now this, as we know, it will store the data in the respective registers. What sub b will do? Subtract b. It means that subtract the contents uh, of b from a. Okay, so it performs a minus b equal to a, and this sub c means what? A minus c equal to a, and this sbb means what? Subtract d as well as borrow from a. Okay, so what it does? It does a minus d as well as a minus. It also subtracts a borrow which was generated due to the previous subtraction. Okay, and in this 8085, the carry flag is acting as a borrow flag when we do the subtraction. Let us execute it stepwise. So with the first step, we have 94 register A. With the second step, we have 84 register B. With the third step, we have 70 in register C, with MVID 06 in register D. Now this sub B will subtract it will perform A minus B, and the content is stored in register A. So we have this 10 in register A. It was 94 minus 84, and we don't have any, so this carry is acting as a borrow. With the next step, sub C, it subtracts the contents of it does subtraction A minus C, and because in this case A was smaller than C, so 10 minus 70, the result is actually A0, and with this carry is actually we have a carry, that is actually we have a borrow. Okay, now with the next instruction, S double B D, that is it does A minus D minus the borrow. So what the final result we get is 99. Okay, and this is due to this A0, okay, minus 06 and minus 1, which was the previous borrow, that is a carry flag. So this is how we do this particular instruction sub and SBB. Now in the second row, we have to do this instruction SUI and SBI. So I have written the code here. So first instruction is MVI A D7, then SUI 56, SBI 67. Now this SUI, it is subtract immediate. It subtracts, it does the subtraction A minus 56, the contents of A minus 56, and the result is stored in register A. Now what is this SBI? Subtract immediate with borrow. So this does the subtraction A, whatever the data is in A, minus 67 minus a borrow which was generated in the previous subtraction. Okay, so let us execute this code. So with both the instructions are of 2 bytes. With the first step, we have this D7 in register A. With the second step, it does a subtraction, that is D7 minus 56, and the result is actually 81, which is stored in register A, and no carry, there is no borrow. Okay, with the next step, it does a subtraction, that is 81, which was the previous difference, minus this 67, and the result is 1A, and again there is no carry, there is no borrow. So if we had a borrow from this previous subtraction, this would also been subtracted from this content, but there was no borrow in the previous subtraction, and even in this subtraction we are not having in borrow. So this is how we get these instructions. Now we come to the second row of instruction of the arithmetic instructions. So we have here INR, DCR, INX and DCX. So now first we will consider INR and INX. Okay, so this is the code which we have written. First MVIB 80, it will store 80 in register B. MVIC FC, it will store FC in register C. And we have INR instruction INR and INC, and let us execute and I will explain it. So with the first step, register B contains 80, so with MVIB 80 gets to register B. With the next step, FC gets to register C. Okay, now with INRB, the data which is in B, it increments by 1. So this INR instruction is for any register. We can increment the content of any register, that is B, A, B, C, D, H, L, any register. It is applicable to any register. It increments the contents by 1. Okay, now with next instruction INRC, so C contains FC, it becomes FD. Now there is one more INRC, it will again increment the content from FD to FE. Okay, now next instruction is INXB. INX, the full form of INX is increment register pair. There are only 4 instructions with respect to INX. One is INXB, INXD, INXH and INXSP. Now this INX instruction, it considers BC as a single register, 16-bit register, and it increments the contents considering them not as 2 different register but a single register. Okay, let us see what happens with INXB. Okay, now as we can see, before INXB the contents were 81FE, Now with INXB it becomes 81FF. Okay, so this considers this 2 as a single 16-bit register and increments the entire count by 1. Now with one more INXB, what happens is, now this FF it becomes 00 and there is a carry which goes into this 8200. So this 81FF, if we add 1 it becomes 8200. So this is how the INX instruction, it considers this entire BC as a single 16-bit register. Okay, and it increments the count with respect to that instruction. Okay, and then finally we have the hold. So this is how INR and INX works. Now we study the remaining two instructions of the third row, that is DCR and DCX. This is the code which I have written. Okay, so let us start with the first code instruction MVID81. So it actually stores 81 in register D. Okay, and with the next it stores 03 in register E. Okay, and see there are three register pairs in 8085. One is BC, DE, HL. So we are considering in the previous INX INR we consider the BC. Now we are considering D. Same is applicable for HL also. Okay, so all these instructions INX and DCX, they are applicable for each and every register pair. Now what happens with DCR? The DCR means decrement. So DCR instruction is applicable for any register. We can decrement the contents of any register by 1. Okay, now with DCRD, the content of D, it was 81, it became 80, it decremented by 1. With the next step DCRE, E was 03, it became 02. Okay, and with next DCRE, the data 2 becomes 1. Now DCX means decrement the register pair by 1. So this DCX considers DE as a register pair, a single 16-bit register, and decrements the content by 1, considering them as a single 16-bit register. See what happens with the next step. Now 8001, now the count decremented by 1, so 8001 minus 1, it becomes 8000. Okay, with the next step what happens is, we can see if we subtract 8000 minus 1, so because this is hexadecimal count, so it becomes 7FFF. So whatever the borrow it gets from here, so 00 it becomes FF and there is a borrow, so we have 7F. So this is how the DCX instruction works. Now next we consider the fourth row. We first consider the DAD instruction, DAD instruction. DAD means double add. Okay, so to understand this, we have written some code. So LXI H1020, LXI D2030, LXI B, and we have these two DAD instructions. So with the first step LXI H1020, so 10 gets stored in register H and 20 in L. With LXI D 2030, 20 gets stored in register D and 30 in E. With LXI B 4050, B 40 gets stored in B and 50 in C. Now what happens with DAD? This DAD instruction is double add. It performs a 16-bit addition. So if we write DAD B, there are 4 DAD instructions: DAD B, DAD D, DAD H and DAD SP. So DAD B, it adds the contents of HL with BC and stores the result in register HL. DAD D, it adds the contents of HL with D and stores the result in HL. So one of the operand is always HL. Okay, the other can be any register pair. So with DAD BC, what happens? So DAD B, it will add the contents of HL with BC and store the result in HL. Okay, so it was in HL was 1020, it was 4050, it becomes 5070. With the next step DAD D, okay, the contents of DE are added with HL and stored in HL register. And next is the halt instruction. So this is how the DAD instruction works. This is the one in which A is not involved. Now the last instruction is this arithmetic, is the DAA. It is called as the decimal adjust accumulator. So what it does, it adjusts the accumulator and it can be used for BCD addition. So it changes the binary values of the contents of the accumulator to the BCD values. Okay, so it can be used to perform the BCD addition. Okay, BCD arithmetic, because in 8085 the numbers are stored in hexadecimal format. So let us see with example. So with the first instruction, you have this example here. So with the first instruction MVIA, so we have this 07 stored in A. With the next step DAA, now because the data is already in BCD format, so 07, okay, 7 is a valid and 0 is a valid BCD code, so we have 07, it does not changes. Now with the next step we have 0A stored in register A, so 0A, now this A is not a valid BCD code, so what it does, it and we can see with DAA this becomes 10, so this 0 is not a valid code, so 10 is a valid code, and A is actually hexadecimal. A is 10 in decimal, so it does this conversion to this DAA. It does the conversion. Okay, so this is how this DAA can be used. So that's all for all this particular session. We have covered the arithmetic instruction in this session. We will cover the logic in the next session. Thanks for watching.